Hello, my name is Vlad Vlaschanu. I'm a database specialist solutions architect with AWS and would like to introduce you today to the features and capabilities of Amazon Aurora that help you accelerate database development and testing. I will spend a few minutes on an overview of the Aurora platform, including the agility-enhancing features unique to the Aurora service itself, then focus the rest of the presentation on 4 key capabilities that make your life easier when developing and testing workloads on AWS. They are Aurora Serverless, fast database cloning, Backtrack, and performance insights. We'll talk more in depth about them in a few minutes. So what is Amazon Aurora? Aurora is a relational database re-imaged for the cloud. We took a long and hard look at traditional databases, their monolithic nature, and decided to address the most jarring issues customers and users struggle with in a traditional relational database environment. Amazon Aurora is designed to match and even exceed the speed and availability of commercial databases while retaining the simplicity and cost-effectiveness of open-source databases. It provides drop-in compatibility with MySQL and PostgreSQL engines, so you don't have to change applications. These capabilities are delivered as a managed service, where you don't have to worry about patching databases, backups, and other time-consuming operational work, and you only pay for the resources you use and when you use them. Why did we decide to give the world another database? The short answer is because our customers asked us to. I want to share a quote from a customer who's been with the service since the beginning. Intuit, as you probably know, is a leading provider of financial management software for consumers, small businesses, and accounting professionals. As they were making the transition from on-premise infrastructure to the cloud, they had to choose a database platform to power their high-end workloads, the ones with the most stringent availability and performance requirements. Before Aurora, the main choice was lift and shift, and while that still yields significant benefits versus running their own infrastructure on premises, they wanted us to explore a database service that truly leveraged the power of cloud. And so we wanted to innovate on behalf of Intuit and other customers who voiced similar requests. So what does reimaging a database mean in practice? We designed a purpose-built, log-structured, highly distributed, and failure-tolerant storage system tuned specifically to database workload patterns. This enables Aurora to scale storage as the dataset grows, providing a high level of durability. Data is replicated 6 times across 3 availability zones in a given region. We've also integrated Aurora with our other AWS services in the ecosystem and automated administrative tasks so you can focus on what is truly important, data design and optimization, and your end-to-end applications. Additionally, we leverage cloud-native capabilities to provide elasticity to your database tier, along with continuous backups. The net effect is that in our testing, Amazon Aurora performed 5 times faster than MySQL and 3 times faster than regular Postgres. We accomplished this using many innovations at the database engine level. For example, we do less work. Databases are normally I/O bound, so our unique storage architecture allows us to do fewer I/O operations. We are also more efficient. We process data asynchronously, batch operations together, use log-free data structures whenever possible. And we introduce new features and capabilities above and beyond what open-source MySQL and Postgres provide. We have instance crash recovery owing to our log-structured storage to minimize downtime during failures, zero downtime patching to mitigate the disruption caused by patching and upgrades, adaptive thread pooling, which allows Aurora to use compute resources more efficiently, and many more such innovations. So how does this help with database development and testing. We spoke with our customers extensively on this topic, and 4 main challenges came to the surface. The first is related to cost. It's expensive to operate at scale databases for development and testing environments, given agile type development methodologies with small teams working independently and in parallel pushing many application updates at a very high frequency into production, especially if these environments are long-running, despite the fact that staff work more or less an 8-hour workdays. So they asked us for capabilities to allow them to scale up and down databases quickly when needed and optimize cost when they are in use versus when they are not in use. Similarly, when you develop and test applications with scale in mind, it's no longer practical to develop and test against small subsets of development data. You need to be able to understand the impact of your design and development decisions on at-scale data and workloads. But replicating environments, copying data, restoring from backup are all very slow processes. This hampers customers' agility, so we built capabilities to give customers fast isolation and isolated access to database copies. So now that customers work with at-scale data sets, it becomes hard to undo mistakes, such as making the wrong schema changes, waiting a long time to restore a data set to the baseline, or recovering from backups, again, hamper agility. So we build capabilities to mitigate these types of penalties. Finally, customers consistently told us that they struggle with performance testing and tracking, both in production as well as in development and testing. Most customers use infrastructure metrics such as CPU, memory, disk I/O to track performance, but at scale it becomes hard to understand when things go wrong, which queries and workload components are causing slowdowns. Sure enough, tools exist to help with that, but having something available directly built into the platform makes things much easier to use. The 4 Amazon Aurora features that directly address these needs are Amazon Aurora Serverless, fast database cloning, Backtrack, and performance insights. Let's see how they can help you, starting with Serverless. Sizing relational databases is hard. You either have to provision for peak usage, which is expensive but handles spikes in usage, or you provision for average use, which is cheaper, but then you hope you can weather the peaks. Neither are ideal, especially in development and testing, where you may have multiple database copies mirroring production scale to meet appropriate testing and validation goals. Aurora Serverless is different. You can create a database cluster without having to specify or commit to a specific amount of storage or compute capacity. The database engine starts up on demand when you start using it and shuts down when it's not in use. It also scales seamlessly to match the load sent to your database engine at any given time without disrupting client application connections. You pay for the capacity you use at the granularity of each second, and you don't pay when the database is inactive. Aurora Serverless is currently available for MySQL 5.6 compatible versions of Aurora. Development and test workloads are primary use cases for serverless because it's easy to provision a cluster. You don't pay for the times, developers aren't using the database, and you can simplify development and test pipelines and CI/CD automations because, again, you don't have to provision capacity, and you can spin up those serverless databases when you need them for as long as you need them. Other use cases are infrequent workloads, like a low-volume blog or content management system, or applications that vary with variable load, where peaks are really hard to predict. Aurora Serverless has a unique cloud-native architecture. Your application talks to a MySQL-compatible endpoint. This endpoint maps to a fleet of traffic routers that queue and manage client connections. and direct traffic to the database engine itself. A database instance handles database operations, and the Aurora platforms continuously monitors the load on that database. When scaling thresholds of CPU utilization and database connection counts are reached, we take a bigger or smaller database instance out of a warm pool of ready-to-use instances, reconfigure it, and substitute it in place of the old one behind the routers. The scaling operation is transparent to the application and takes about 5 seconds. You configure the minimum and maximum capacity you wish to scale between, and whether you want the instance to be paused completely when there's no database activity. Throughout the lifetime of the serverless database, your data is durably stored using our purpose-built storage service. I already mentioned you only pay for what you use while the database is active. We measure capacity in Aurora capacity units, and there's a flat rate per second of Aurora capacity unit usage. Depending on the number of capacity units you consume every second the database is active, with a 5-minute minimum each time the database is activated. Storage and I/O is based on the amount consumed, same as with regular Aurora clusters. So let's look at the demo. I'm going to show you how to create a serverless database, connect to it, and even how it scales in response to load. I'm going to go to the AWS Management Console. I've already logged into it just to save time, and I'm going to browse to the RDS Management Console under Databases. And right from the dashboard of that console, I already have the opportunity to create a database. There's many ways and many places you can create a database through the console, so I'm going to pick the easiest one and just click this orange button that says Create Database. And I am going to pick our Amazon Aurora as our database engine. And if I scroll down, I'm going to make sure that MySQL 5.6 compatible is the selected edition. Then I'm going to click Next. And on the configuration screen, I want to make sure I pick serverless as the capacity type. You'll notice that with serverless, I don't have to specify any database instance classes from a capacity perspective. I'm going to provide an identifier for the database and a master username. And a password. And then click Next. On the advanced configuration screen, I get the opportunity to specify my desired minimum amount of Aurora capacity units and the maximum Aurora capacity units. These are the two values that our cluster will scale between. You can go all the way up to 256 capacity units. In my case, I'm going to pick 64 capacity units. I'm also going to provide the correct networking configuration with which VPC I want to launch into, the subnet group, and the relevant security groups. And that's all I had to do to configure it. Now, in the interest of time, we have pre-recorded some of these demos, and I already have a cluster running just to save the few minutes that it would normally take to launch the cluster. So I'm going to hit cancel here and just go to my existing Aurora cluster. You'll see here I have a database, a serverless database called Serverless Demo. If you're scrolling sideways in this listing, you'll see that it has 0 capacity units, meaning it's inactive at this point, and it's of type serverless. So I'm going to go ahead and connect to this database and start using it. Now, because the database is inactive, the first thing you will notice is that it will take a few seconds for my database connection to get established. It takes about 20 seconds for that initial database connection to be established. During this time, the Aurora service is going to take and provision capacity out of a warm pool for our database and bring and reactivate my database. Now again, the data is stored durably on our Aurora storage, so these processes do not affect the persistent data that you're storing in your Aurora cluster, just the availability of the databases. During scaling operations, this time is going to be also significantly shorter and you're not going to notice as much of a delay. So, okay, our database is connected. The serverless cluster has been spun up, and you'll notice behind the scenes here that I actually have a cluster that already has been instantiated. Now, initially, when you're actually spinning up a cluster, when you're activating a cluster, we're going to allocate more capacity to your cluster than your minimum, just because we do not know, how much load you're going to initially send to the database cluster. So now I can go ahead and start using the cluster. It's like any other regular cluster. Okay, so one thing I wanted to also show you is how this cluster scales over time. So I can go back in the dashboard in the RDS console, under select the serverless cluster, and you'll notice that on the detail screen it's going to have information about capacity, and it's going to pull in charts and graphs based on the load on those clusters. Now, in my case, this cluster was inactive for quite a bit of time, but if I go and look at more details around this cluster and go back in a time range of, say, 6 hours, you'll see that the capacity scaled up and down several times as I generated load against this particular cluster. So the next compelling feature for accelerating dev and test workloads is fast database cloning. We wanted to give customers faster access to copies of their data so that they can iterate faster in their development life cycles. This can make testing and pre-production easier on relevant at-scale data sets. It can help you reorganize databases or make schema changes with minimal impact to production. It can also give you the ability to create effectively a point-in-time snapshots of your data that you can then use for heavy analysis, again, without impacting production systems. Fast database cloning allows you to create clones of your database cluster without having to copy the data. This feature is available for both MySQL and PostgreSQL compatible Aurora engines. And for both, the clone creation process is nearly instantaneous, regardless of the size of the source database. Data copy operations occur only on write, and when you make a change to either the original or cloned dataset. That's when the data in the storage volume starts to diverge. It is effectively a copy on write system, where our purpose-built storage service keeps track of the location of data and doesn't duplicate data that's not different. As a result, you only pay for the storage difference consumed on the clones, and not for an entire new copy of the data. This makes creating dataset copies for development and testing both cost-effective and fast. You can have up to 15 clones directly or indirectly derived from the same source. And operations on the clone do not affect the source cluster or any of the other derived clones for that matter. Here's how fast database cloning works in practice. Going back to my Amazon RDS console, on the left-hand side in the menu, I go to Instances, and I already have a source instance here, which contains essentially a copy of the Wikipedia, the public Wikipedia data set. This is an instance that's about 250 gigs of storage, consumes about 250 gigabytes of storage. So it's not a small database, but certainly not a huge database either. It's pretty common to what sizes of database we see customers are operating. So I'm going to select the Wikipedia demo database, and under Instance Actions, I'm going to go ahead and pick Create a Clone. I'm going to click that, and I'm going to provide similar specifications and settings as you would when you create an entirely new database. I'm going to give it an identifier this time. I'm going to make sure that the networking configuration is correct, including the security groups. And I'm going to accept all the other defaults. Now, really, you don't need to provide any more configuration details than that. A lot of the configuration details are inherited from the source. And when I'm ready, I'm going to go ahead and click Create Clone. And the system is going to provision now a new database cluster, a new Aurora database cluster, but it will leverage essentially the same data and it will point to the same storage structures as the source database. That way, no data duplication occurs. Now, even though we're creating a new cluster and we're not copying any data, it will take a few minutes to create this cluster. And just to save time, also pre-recorded this demo. Demo cluster got created, our clone got created. So what I'm going to do right now is log in both the source and the clone, and see how the data starts to diverge. Switching back to my console, I'm going to log into my source cluster first. All right, then I'm going to simply create a schema. All right. If I do show schemas, I can see this new schema that I just created. I'm going to quit and then log into my clone. I'm going to run show schemas, and you'll notice that the schema that I just created on the source did not show up on the clone. The data sets diverged at the point when we actually created this clone. So I'm going to create a schema here as well. And as expected, you'll notice that the new schema that I just created shows up here as well. So essentially, your clones are diverging at the point when you actually created it, and you can use the clone for a variety of use cases independent of your production data. Okay, so now that you see how easy it is to create clones of a database, let's talk about Backtrack. We built this feature to offer customers a fast and easy way to undo changes to data. With this feature, the risk of implementing changes to databases at scale is reduced, as you can easily undo unintentional or unanticipated DML or DDL changes, for example. It also mitigates the risk of malicious actors changing your data without your permission. And for all this, you avoid time-consuming data restore processes from backups. Backtrack works by taking advantage of the log-structured nature of Aurora storage. Any given Aurora storage volume is made up of many independent segments. We keep periodic snapshots of these segments, but also preserve a log of change records to these segments. For Backtrack, we simply identify the appropriate segment snapshots, then apply the log stream to the segment snapshots in parallel and asynchronously. And effectively, this allows you to rewind the database to a desired point back in time. Backtrack is not destructive. We simply hide the snapshots and logs that are later in time past the point of recovery, so you can backtrack multiple times to find the right spot. The diagram above illustrates also how you can backtrack multiple times. On the initial green timeline, at time t2, we decide to rewind the database state to reflect the database, how it looked like at time t1. All changes after t1 become invisible. And at T2, we start making changes to the data diverging from what T1 looked like. Again, at time T4, we decide to backtrack again to the state of the database as it looked like at time T3. And we can continue this change going so on to make adjustments to our data as needed. You can configure the desired duration you can go back in time for, up to 72 hours, and you pay for the amount of change records retained for your database during that desired duration. Backtrack is available for the MySQL 5.6 compatible database engine of Aurora. Let's look at what it means to fix a mistake in your database using Backtrack. So I'm going to switch back to my RDS management console, and I'm going to show you how to create a cluster with Backtrack enabled. The creation process is similar as before. We choose the Amazon Aurora database engine. We make sure the edition is MySQL 5.6 compatible. We click Next, and for this time, we make sure we choose the provisioned capacity type for Aurora. We choose the desired database instance class as well as multi-AZ configuration, provide a name for the database, an identifier, as well as the master username and password. And then click Next. We configure the correct networking and security settings. And as we scroll down through the list of available and advanced settings of the database, you'll notice that there's a section called Backtrack. And here we choose the option to enable Backtrack and specify the desired amount of hours we want to retain change records for, which effectively is also the window of time that we can backtrack and rewind the database back. I'm going to pick 24 hours. And at this point, we can go ahead and create a database. Now again, I've already created a database just to save us the few minutes that it would take Amazon Aurora to provision our cluster. So let's look how Backtrack works in practice. I have this cluster here called Backtrack Demo, and I'm going to go ahead and connect to it using the command line tools. All right, now this database contains a demo data set of the employee database, a generic employee database that is available for my SQL database engines. So I'm going to go ahead and start using that database. You can see the database available. All right. And what I'm going to do is add myself as an employee of this fictitious company. And I'm going to give myself a salary as well. And I'm just now noticing that I've been a little bit too generous with my salary and made it a little bit too big. So what I'm going to do now is try to fix that salary problem. And oops, it seems like I made a mistake here. I'm just now noticing that this query will takes a little bit longer than I intended to. And I realized I actually didn't put a predicate in it. And that's a problem because I have about 2 million salaries in this database, and I'm going to reset basically every one of them right now to the same number. It's clearly a bad mistake, can be quite impactful. So we need to fix that. Now the options to fix that traditionally would have been to go and use point-in-time restore to roll back the database and restore from a backup at the point in time before I started making these changes. Now that would normally be very time consuming, especially very large databases. So what I'm going to do is use Backtrack instead. I'm going to exit out of the database. And I am going to go ahead and go to instance actions for my Backtrack database here in the RDS management console and choose Backtrack database cluster. Now the system is going to helpfully tell you how far back in time you can go and what's essentially the earliest restorable time. Again, this webinar being pre-recorded, I'm picking a closer time just a few minutes ago. And I am going to make sure that I can restore the database and click Backtrack Cluster. Okay, so this operation will also take about a minute or two to complete. And in the meantime, what the Aurora system is doing, it's going to go ahead and essentially identify those segment snapshots that we talked about earlier that are relevant to our point-in-time restore point, and it's going to go ahead and apply all of those change records to get to the precise point in time that I have specified there, in that case being 1 p.m. 54 minutes 56 seconds. All right, so our cluster just backtracked. So now we can go back into our database, connect back to our database, and start using it again. Let's see, where did we replay back? All right, so if I'm trying to find my employee record that I've entered, it's not there yet. So what that means is I've actually gone a little bit too far back in time. But that's okay. What we can do is exit out again and try this again. Now, sneakily, just for the purposes of this demo, I recorded timestamps when I made these operations, so I can easily go back in time just to the right spot. So I'm going to go back to the RDS console, back to my cluster, and I'm going to pick instance actions, choose Backtrack Database Cluster, and try again. and be a little bit more precise as far as the time that I want to choose. And I'm going to go ahead and backtrack database cluster. Now again, the process may take about a minute or so. And again, the system's going to go back to those segment snapshots, identify the right ones, apply the change records, and effectively rewind the database. In this case, it actually is going to play it forward a little bit, move that pointer a little bit forward, because I went back in time a little bit too much. All right, so I've successfully backtracked again. The console helpfully confirms that the process has completed. So I'm going to go back into our MySQL console and see what state my database is in at this point. I'm going to use the employees database, and I'm going to try to find my personal record. And sure enough, I am in the database. But if I go ahead now and try to, let's look at the salaries, see if they're correct this time around as well. Perfect. So now you can see a bunch of different records. I just ran a simple query selecting the first top 20 rows. I'll see that the salary value is actually different. So you can see with this demo how you can finely tune and jump back in time and rewind and find the exact spot that that is relevant if you've made a mistake. The last feature that I'd like to spend some time on is performance insights. Until now, we spoke about features that make working with databases easier. This feature helps you gain better insights into the queries running on your database and their performance profile. There are many reasons to monitor the performance of your queries. No workload is rigid and unchanging. Workloads change over time in terms of feature enhancements, volumes of data, or usage patterns. As such, design decisions at one point in time in the past may no longer produce the most optimal results sometime in the future. So you should establish a baseline of acceptable or desired query performance for key and common queries in your application. That way, you can assess the performance impact of changes to your workload. This, in turn, informs future changes that might be needed and will help you troubleshoot poor performance as well. And will also help you identify bottlenecks, whether they are in your queries or in your available capacity. Thus, you can use query performance monitoring as a way to inform capacity planning decisions as well. But query performance monitoring is non-trivial, and often the tools are complex and require deep understanding of database engine internals to derive meaningful insights. Performance Insights, however, provides an easy-to-use and powerful dashboard that gives you insight into which queries and which wait events are consuming your resources. You have access to an adjustable time frame, and 7 days worth of performance data history are provided for free when enabling the feature. This is ideal for dev and test use cases, as the free tier is sufficient for most customers wishing to analyze performance and troubleshoot performance issues. However, for more complex needs, we offer the ability to retain up to 2 years worth of long-term data, history data, priced per virtual CPU per month for each database instance in which it is enabled. Performance Insights is available for Aurora Postgres and Aurora MySQL 5.6 compatible database engines. So let's look at how some of these dashboards look like. Since we've done some activity in the database, part of our previous demos, I can go ahead and look at my databases and see see some of the performance metrics. To access performance insights, on the left-hand side menu of your RDS management console, you pick Performance Insights. And you'll see that all of the database instances that were enabled for performance insights and you can access performance data for are listed on the left-hand side. So I'm going to pick the Backtrack Demo database. We've just done some changes to that database and I actually had performance insights enabled for it. So we can see that it's mostly inactive as a database. But there's this little spike of usage right about the time I actually was making changes to the database and accidentally changing all the salaries. You can also see where the system spent most of its time. CPU load versus all the other types of weights that affected the response time of your queries. So this dashboard, you can move around it, you can zoom in and zoom out. There's also a reference line here for maximum virtual CPUs that gives you a reference point as far as what's the total compute capacity in relation to the sessions that are displayed on the vertical axis. If you scroll down, you're going to see a breakdown of the different performance data by weights, by SQL queries, by hosts or users. So I can see, for example, what are the top weights on that system at any given point in time. In this case, it's a SQL table IO table handler. Obviously, this database doesn't have that much load on it. I can see by query. In this case, this is my update query. I also can look at hosts and users. In this case, there's not much load on this server. But let's look at the server that actually has significant load on it. Prior to this demo, I have run a sysbench test, a load test on this particular database called perf-ins demo. And you can see how these metrics look like when you're looking at a database that is, to be honest, under provision for the amount of load that I actually send to it. So you'll see much more variability in the type of weights that get displayed in the system, many more locks and mutexes that show up, and you'll see that the CPU load is above that reference line of max vCPUs. That should give you the idea that this instance is likely under, extreme load and you need to actually provision a larger instance for this particular workload. And again, you can see a breakdown of those weights based on the queries that are executed by the system. You'll see, for example, that commit predominantly the weight is the Aurora redo log flush, which could signify that your instance may not have enough network bandwidth for I/O purposes. CPU comes up in your select queries. You can also order and see what the most common weights are. You can also understand what the hosts are, which hosts are generating the load. In this case, it was a load testing workload, so most of the load should be relatively even spread across all the hosts. But this is important. If these numbers aren't similar in your workload, that either means that there's different workloads attaching and querying your database, or there could be some efficiencies with some of the issues with some of the hosts. But it will give you a good idea of what type of performance problems you could expect and what you should optimize. In this case, CPU being one of the elements and the other one being networking throughput for I/O purposes. So to summarize, we've learned how Amazon Aurora is a database engine built for the cloud, with many capabilities meant to simplify operations. We've also discussed what it takes to accelerate database development and testing. Using unique Aurora features such as Aurora Serverless, which allows you to create databases without having to provision capacity ahead of time, and which scales automatically to meet database load. Fast database cloning, which enables you to create clones of your database regardless of the size without having to copy any data over from the source. Database Backtrack, which enables you to quickly undo mistakes by effectively rewinding the database state to a point in time. And Performance Insights, which provides out-of-the-box query performance monitoring capabilities without the need for external tools. Amazon Aurora provides many more features designed to make operating high-throughput databases at scale as easy as possible. I recommend you visit our website at aws.amazon.com/rds/Aurora and also tune into future webinars that will discuss Aurora capabilities. Thank you very much for listening, and we will answer now questions that came through the QA channel.